Okay, guys, now I am recording one more session on section 3.3, that is the graph coloring. And again, we are going to do some important definitions and some concepts in this. So, and please go through this. And I'm posting one more 5-minute video from YouTube as well. That's not created by me, but I thought that covered some important concepts really nice. So, let us start 3.3 then. At this point, I am assuming you all know basic definitions pretty well. So let us start with the PowerPoint. I'm assuming you all can see the PowerPoint. So we are starting section 3.3, that is graph coloring. And again, most of the textbooks uses the word vertex coloring, not the graph coloring, but both means the same thing. That means you're coloring the vertices of the graph. Let us start with and review some of the basic definitions you had seen before. Please remember, throughout this section, your graph is not a digraph. It is just a regular graph with no arcs, just no directions or anything, and has no loops, no multiple edges. So this is just a simple graph. So the definition of complete graph is, take a graph with a bunch of vertices. If there is an edge joining every any two of them, that is called a complete graph. This is a complete graph on one vertex. This is a complete graph on two vertices. There are three vertices and there is an edge between each and every of them. So that is 3. There are 4 vertices and there is an edge between each and every of them, so this is K4. I'm sorry guys, this is not K4, so this is a mistake there. Let me cross it out. This is not K4, so this is K4. So I'm assuming everybody is comfortable with the definition of a complete graph. So take some vertices and between any two vertices there is an edge. Now this is ZP means circuit on P vertices and P edges. That means this is simply a cycle or a circuit. Most of the textbook uses C, but our textbook uses Z, but both means the same. This is a circuit on 3 vertices. This is a circuit on 4 vertices. This is a circuit on 5 vertices. That means this is a simple circuit. Now, another definition which you note is bipartite graph. A bipartite graph means this is a graph and I can divide the vertices into two different parts. One is U and the other is V, and the edges only go from one side to the other. For example, there is no edge between any two vertices in U and there is no edge between any two of them in V. These are completely disconnected, but there is an edge between U, one vertex in U and one vertex in V. Please remember, not all of them are connected to each other. For example, there is from this point, I'll call this 1 here and I'll call this 4. There is no edge connecting between 1 and 4. But all I'm saying, if there is an edge in this graph, it is going from one set to the other, not within. That means I can partition the vertices into two parts. It is called a bipartite graph. Now I'm going to give you one more definition. It is called a complete bipartite graph. That means I can partition the vertices into two parts and edge is always going from one part to the other, and but everything in one side is connected to everything in the other. For example, if you see this, this is connected to this, this is connected to this, this is connected to this, and this is connected to this. So this has a complete graph with two parts. On one side there are three vertices, then the other side there are two vertices. So normally we will call this as K32. K25 means there are two vertices on one side and 5 on the other side, and there is an edge between each and everything, every possible way. So this is connected to 5 of them, this is connected to 5 of them. So the total number of vertices in this case are going to be 6. Total number of edges is 3 times 2 is 6. I'm sorry, total number of vertices is 5. In this also, total number of vertices is 7 and total number of edges is 2 times 5, that is going to be 10. You can count it, that is the formula for it. So these are the basic definitions. Now let us go into the concept of graph coloring or vertex coloring. Graph coloring or vertex coloring. Okay, let us go to this. Take any graph. Okay, this is the graph I drew, so it doesn't matter. What is the meaning of this graph is K colorable? That means if I can color the vertex using at most K colors. For example, instead of coloring them, I call colors as 1, 2, 3, and 4. The way you need to color it is, if there is an edge between any two vertices, you cannot give them the same color. For example, I call color this 1. So I cannot color this as 1 because there is an edge going on. So I put 2 here. And I say I can put, say, for example, 3 here and a 4 there. And here, this I can color as 3 because there is no edge. So this graph I colored by using 4 colors. So I'll call this as 4 colorable. Of course, I can also call this as 5 colorable also, because the definition of k colorable is as long as I used at most k colors. So I can call this as 10 colorable, because as long as I use total of colors less than or equal to 10, I am good. So frankly, I can color each and every vertex with a different color. So I can increase the number of colors all the time. So this graph is 4 colorable. How many vertices I have? 1, 2, 3, 4, 5. So I can call this graph as 5 colorable. Even I can call this as 10 colorable, because as long as the number of colors I use less than or equal to 10, I'm fine. I am using 5, which is less than 10, so I'm good. So k colorable is not of very much interest. So the most interested question in this is, what is the fewest number of colors I can use? What is the fewest number of colors I can use? That means as few colors as possible, you need to color each and every vertex. Let us go back to this exact same graph. Let us try to color it. I'll color this as 1. I'll color this as 2. Now I can use the same color as 2 here because there is no edge between these two. Now I cannot use 2 here, but I can use 1. I'm trying to use as few colors as possible. Now I have to use, I cannot use 2 and I cannot use 1, so I am forced to pick a different color. So I don't think I can color less than 3 colors, because the degree of this is 1, 2, and 3. So this vertex is connected to 3 different vertices. So at least I need to use 3 colors at least. So I achieved. So the chromatic, this number is called the chromatic number of the graph, and it is denoted by this symbol. In this case, the chromatic number of this graph is going to be 3. There is wide variety of applications for this. Just imagine you're scheduling final exams for your school. You can imagine these, each and every vertex is nothing but a section, and you join 2 sections if there is a student which is in both the classes. So when you are scheduling an exam, you want to make sure you cannot schedule exam at the same time for these 2 classes, because there is a student which is in both of them. So if you want to accommodate him, what you want to do is you put a vertex for each and every section, and if there is a student in both the classes, then you will join them by a vertex. For example, there is no student which is common here, this class and this class, so both of them can have the final exam time at the same time. So that is a typical example. So fewest number of colors means with at most 3 time slots you can schedule all the final exams. Or you can think of this as a committee problem. So you want to schedule a meeting times for the committees. Each and every committee is a vertex, and if you join them, if there is a member which is in both the committees, so you have to make sure those 2 committees have meeting times at different timings. So hope I'm making sense here. So the chromatic number in that case is the fewest number of time slots possible, which you can do that. So that is the definition of chromatic number. So I strongly recommend, please read the examples from 3.11 to 3.15. I think these are all on starting from page 145. All these examples are there. Please read it. It won't take much time, so please read it. Now let's go to the next definition. I'm assuming you're all comfortable with chromatic number. Let's go to the next definition called clique. Clique means, take any graph, take some of the vertices such that there is an edge between any of them. That means, for example, let us change this graph a little bit. For example, let us take this graph. For example, in this graph, ABC is one click, because this is some collection of vertices in this graph, and there is an edge between AB, AC, and BC. Similarly, BCD is one click. Similarly, ABCD is one click. These are all different clicks. That means these are all subgraphs of this graph, and which are complete. So you can think of this as a sub-complete graph. Again, I'm not being very formal here. That means you take some set of vertices such that there is an edge between any two vertices. But if you take, for example, C, D, E, this is not a click. You can clearly see that there is no edge between C and E, so this is not a click. So A, B, C, D. So you wonder what is the biggest possible click, and that is called the click number. In this particular example, A, B, C, D is the biggest possible click. So if you take any 5 vertices in this case, they are not going to be pairwise adjacent. So for this particular example, click number, that is denoted by omega of G, is going to be 4 for this particular graph. So there is a nice connection between chromatic index and the click number, because if you take this click ABCD, since everything is connected to, there is an edge between any two, if I want to color the vertices, all these 4 should get different colors because there is an edge between any of them. So if I want to color this graph, I need at least 4 colors. If I want to see this, for example, if this is color 1, this is color 2, this is color 3, this is color 4. So at least I need 4 colors. Maybe these 4 colors sometimes is sufficient, sometimes you might need more colors. But I think in this case, I can put 1 here and I can put 2 there. I think chromatic index in this case is 4, but sometimes it can be more than that. But one thing is certain, chromatic index is all the time greater than or equal to click number. Okay, you can try a couple more examples. I'm going to post some in the assignment. Now the next definition we are going to see is called the independence number. I think I forgot to draw this edge. Take the same graph. Now click means, if you go back, it is a sub-complete graph. That means it is some set of vertices where everything is connected to everything. When I use the word connection, between any two there is an edge. This is one extreme. The other extreme, independence number. That means I want to take some set of vertices such that everything is pairwise disconnected. That means there should not be any edge between any of them. That is called an independence number. For example, in this case, AE is an independent set because there is no edge between A and E. And for example, I can say CEF is one independent set because there is no edge between C and E, there is no edge between E and F, there is no edge between C and F. So these all are independent sets. Now we are interested in figuring out what is the biggest set possible, and that is called the independence number, that is denoted by alpha G. What do you think is the biggest possible independent set? In this case, that is going to be 3. For example, take any 4. All 4 of them are not pairwise disjoint. When I use the word disjoint, that means there should be an edge somewhere. So if you take any 4 vertices, it is impossible to find 4 vertices in this particular graph. So for this particular graph, independence number is going to be 3. So click is one extreme and independence number is the other extreme. There is a nice relation between click and chromatic index. Similarly, is there any relation between independent set and chromatic index? You can see that since A and E, I can give the same color because there is an edge. For C, E, and F, I can color all of them using with the same color. So there should be a link between independence number and a chromatic number. And that relation is not as straightforward as this, and that relation I'm going to prove in the next slide. This is the result. This is alpha g is the independent number, and v of g absolute value is total number of vertices in the graph, and this is the chromatic index. This is not very obvious like the previous result, but I'm going to prove it and it makes more sense to you. Take any graph, imagine it has n vertices. Okay, this has n vertices. Now I'm going to give you a proper coloring. That means I color each and every vertex. If there is an edge between any two vertices, they should be assigned a different color. Now I'm going to partition into color classes. That means pick up all the vertices. If they have the same color, group them together. That means maybe these are all same color. These are all same color. These are all same color. Since the chromatic index number in this case is going to be k, that means if you group like this, there should be k color classes. That means this is all color red, this is all color blue, like that. So there should be k of them because you used k colors. So this is say 1, 2, and this is the kth set. There are k sets. Please remember each color class is an independent set because they all have the same color. There is no edges going on between any of the two. So there are total n vertices and you divided them into k pieces. So on an average, the size of each piece is going to be n divided by k. That's what I'm saying. On an average, there are n things and I'm dividing them into k pieces. So on an average, each of the size is going to be n over k. But I'm saying, so there should be at least one set which has total number of vertices is at least n over k. That means at least one of them as total number of vertices is more than or equal to n over k. That's what I am saying. Because if I prove it, that means I found a set of vertices which is bigger than this, and there is no edge between any of those two. So the independence number is at least this much because I found one independent set. So then I am done. How to prove there is at least one independent set of size? This is where the pigeonhole principle comes into place. I am proving suppose not. So this is the proof of this piece I am proving. Suppose not. That means the size of each and everything is strictly less than n over k. This is a similar result you proved in previous assignment. What that means? Size of each color class is strictly less than n by k. That's what I wrote. Now you count all these vertices. If you count all of them, I'm going to get total number of vertices. That is going to be n. And I'm saying the size of each and everything is strictly less than n by k. So if you add all of them, that should be strictly less than. I'm adding n by k. How many times I'm adding? I am adding k times because I'm divided that into k different things. And size of each and everything is less than n over k. So if you add all of them, that should be strictly less than n over k plus n over k. I'm adding k times. That means adding anything k times is exactly same as multiplying that by k. These two will cancel out. So I got n is strictly less than n, which is a contradiction. So my assumption that each and every color class has size is strictly less than n by k is wrong. So there should be at least one whose size is greater than or equal to n by k. So I got my result. Hope this makes some sense. So now so far we defined three definitions. One is the chromatic index, and the other is called a clique number, the other is called an independence number, and the relation between them you have seen. So now let us look into it. Calculate the chromatic number of different graphs. For example, take a complete graph on 3 vertices. Since there is an edge between any of them, I need 3 different colors. Complete graph on 4 vertices. There is an edge between any of them, I need 4 colors. So in general, complete graph on n vertices, the chromatic number is n. Some people call chromatic index, some people call chromatic number. So I'll be using these terms interchangeably, so please understand. So if you take any bipartite graph, that means the graph is going to look like this. There are two parts U and V, and edges are always going in this direction. So I can color all these with one color and I can color all these with another color. So it doesn't matter the size of the graph, chromatic number of a bipartite graph is all the time 2. So for a complete graph, it is n. For a bipartite graph, it is 2. But in general, if I give you any graph, so if I give any graph G, and I ask, okay, is this graph is k colorable, or that means is this graph is 7 colorable or 8 colorable? That problem is NP complete. What exactly that means is that problem is very difficult to answer. There are some problems in math called NP complete problems. Nobody knows whether they're right or wrong. If you can prove one is right, all of them are right. If you prove one is wrong, all of them are wrong. So if any of you can come up with a solution to prove either one is right or one is wrong, that means you have solved like a bunch of problems where either all of them are right or all of them are wrong, and you are going to be very, very rich. Okay, most of our internet security and banking security, everything depends on the fact that NP complete problems are not solvable. If you solved it, that means you did a huge thing. So a chromatic number given the graph is k colorable is NP complete problem. This is not such an easy problem to solve. For some graphs you can do it, but in general you can't do it. But one thing you can do, you can say is, can you say graph is two colorable? That you can do. A graph is two colorable if and only if it is bipartite, and it is, and this is extremely easy for you to prove. And I think if the graph is bipartite, just now I discussed, you can put two colors, for one for each part. Suppose if the graph is two colorable, then also you can prove that is bipartite, because group all the terms or group all the vertices with one color together, and that is going to be one part, and group all the vertices with another color, that is going to be in another part. So this proof I am going to leave it to you for you to think about. This is extremely easy one-line proof. And another thing is, a graph is two colorable if and only if it has no circuits of odd length. And the proof is given on this page. You can go through that, but it is extremely nice and simple to see. Take any odd circuit, for example, say 3. I cannot color with two colors, I need 3. For example, take a circuit with 4 vertices, then I can do this 1, 2, 1 and 2. 2 colors is enough. Take for example circuit of length 5, 1, 2, 3. Then I cannot color with 2. So for example, this is 1, 2, this is 1, 2. Then I cannot color this 1 or 2 because of this. So I need 3 colors. So if the graph has an odd circuit inside, then you cannot color with 2. And this is also very straight and simple proof. I want you to go through that on this page. And this is just one line things. Okay. Now, so I'm assuming you're all comfortable with the chromatic number of a given graph. Now there are variations of this which is most useful. That is what I'm going to talk about now. One of the variations we are going to talk about is called a T coloring problem. I will explain with the help of an example. So let us take, for example, you have a bunch of television transmitters, and they are all, for example, this is the graph. And you want to assign a channel to each television transmitter. That means you can think of this as CBS, this as ESPN, this is CNN, like that. And one thing is, if the transmitters are within 100 miles, you want to give them different channel numbers because of the frequency issues. You want to make sure you get in different channels, right? So now you want to design a graph for this. So I call each vertex as one transmitter, and there is an edge between any two vertices if they're within 100 miles. That means A and F are more than 100 miles, so they both can come in the same channels because they come in different regions. So now you want to see, well, how many fewest number of channels I can use. So I'll assign this channel 1. This is channel 2 because they're within 100 miles. This is 3 and this is 4. Okay. And since these two are not within 100 miles, I can give channel 1 here and I can channel 1 here. So the chromatic index for this graph is going to be 4. So I can, with 4 channels, I can cover all these transmitters. This is just a regular chromatic number problem. Now I want to put a restriction. Now I said this. They are not only get different channel numbers, but the difference between the two channel numbers has to be certain thing. That means the difference has to be little bit. You are setting up something. They cannot differ by certain values. You will call that as a forbidden differences. I will explain with the help of an example. Take the same thing. Now your t in this case is 0, 3, 4, and 7. That means if I give channel number 1 here, then this cannot be B cannot be, I cannot give B to 1 plus 0. I cannot assign B channel number 1. I cannot assign channel number 4. I cannot assign channel number 5. I cannot assign channel number 8. I mean, they have to be separated by so and so. That means because of the bandwidth issues. This is what realistically it will happen. That means I cannot assign B as 1, 4, 5, and 8. So maybe I'll assign 2 here. Once I assign 2 to B, I cannot give for channel C 2 plus 0. I cannot assign channel C as 2, 2 plus 3 as 5, 2 plus 4 as 6, 2 plus 7 as 11. So I cannot give these numbers to these. So if you can do for this, so that you will give a color, you will give a number to each and every transmitter or a channel, so that they are not only different numbers, but they should not differ by certain values. That is called a T set. And if you can do that, that is called a T coloring. Always 0 is part of your T, because if 0 is not part of your T, I can give same color to each and every channel, and that is not even a proper coloring to begin with. So 0 is always belongs to T. 0 is always in T. So if you can do like this, each and every channel should get a different color, and also they cannot differ by certain values. Then if you can do that, you'll call that as a T coloring. One of the easiest ways you can do this is, and one of the lazy ways is, I'll put 1 and 2 here, and I'll assign them far off. Say maybe I will give you this as a 100, this is 500, this is 1000, and this is 2000. These are the channel numbers. So since they are so far off from each other, so certainly they satisfy your requirement. So I used how many different colors? 1, 2, 3, 4, 5, 6. So I gave a 6 coloring. This is not very efficient. This is certainly a T coloring, that's for sure, because you satisfied the definition, but this is not very efficient. What is the meaning of efficiency here? You used 1, 2, 3, 4, 5, 6 different colors. If you can do with smaller number of colors, and that is efficient. There are two ways you can do efficiency. One thing is I use too many colors, that is one screw up, and one thing is they're far off. If I want to press this, I need to press channel 2000, and this is channel 1. So they differ by far. So the channel numbers better be close to each other. It is screwed up in that span issues, and I use too many colors. So it is screwed up efficiency in two fronts. So what is the meaning of efficient way of T coloring? One of the ways is, if I can use as few colors as possible, then that is called T chromatic number. Take the same graph. In this case, I'll call the same T 0, 3, 5, and 7. Now I want to use as few colors as possible. Okay, let us do this. 1, 2. So then this cannot be. Let me check. So let's make this 4 and say 3, 1, and say for example 11. This is one coloring. You can see that it satisfies the requirement. But is this the fewest number possible? Can you color with smaller colors? I think the answer is yes. For example, I can color the same. I can both of them. They are not within 100 miles of 1. So frankly, I can remove this and color this with 1. So though I used 5 coloring, in this particular case, the T chromatic number in this case is going to be 4 because I used 4 different colors. The colors 1, 2, 3 and 11. You can see that you cannot use less than 4 colors because these 4 vertices are adjacent to each other. So you need at least 4 colors and you used 4 colors. So the T chromatic number in this case is going to be 4. So one of the nice results you are going to see is for all graphs, and it doesn't matter what is G and what is any T set, these two are going to be the same. These two are going to be the same. Okay, these two are going to be the same. I think I am disconnected there. Let us share again. These two are going to be the same. So let us prove this with the help of an example first. Take the same graph. Take the same graph. Take the same graph. If you can give any T coloring, in this case T is going to be 0, 3, 5, 7. If you can give any T coloring to this, for example, in this case I already gave 1 before. Let us use the same thing. 1, 2, 3, 11, 1 and 1. These are the colors I gave. So any T coloring is obviously going to be a proper coloring as well because 0 is a part of it. So two adjacent vertices cannot be the same color. So any T coloring will obviously going to be a proper coloring also. So this is true. So once I give tree coloring, I'm going to get a proper coloring as well. But the chromatic number is the smallest possible of those. So that is what that is. So this is the proof. 0 is always contained in any T set. Any T coloring will be a proper coloring. Now going the other way, suppose I give a proper coloring. Can I come up with a T coloring? Let us take this. Same graph. Let us draw the same graph. Give a proper coloring to this, but this is our T. I call this 1, 2, 3, 4. And I'll call this as 1 and say 1. This is a proper 4 coloring. Now I want to give a T coloring. The way you need to do that is take each and every color and replace that with, for example, take color 1 and you replace that with 1 times. What is the biggest number in the T set? That is 7. You multiply that by 7 plus 1. So that is 8. So you replace color 1 with 8. Similarly, you replace color 2 with 2 times 8 is 16. You replace color with 3 times 8, 24. You replace color with 4 times 8, 32. And this is 8 and this is 8. This is a T coloring. And I used exactly 4 colors, but the color numbers are different. And since I used the biggest possible number, that means I picked far away numbers. And I used as few colors as possible. It's certainly the span is not, these are not the smallest channel numbers, but this is certainly a proper T coloring. So once I came up with any proper graph coloring, that gives rise to a proper T coloring also. That is the proof here. Consider any proper coloring. I can assume those colors as 1, 2, 0, replace color I at a vertex with I times T plus 1, where T is the largest number. This is going to form a T coloring. So I proved each one is less than the other, so they are equal. So in this case, this is, for example, if you look into this, 8, 16, 8, 24, 32, it is a proper T coloring. So this is efficient in that sense where I use the fewest number of colors as possible. Now another way of efficiency is span. That means I want to use the smallest number of colors as possible. smallest number of colors. That means smallest channel numbers, I mean to say smallest number. So for example, if you take the same graph, if I take the same graph, this is color A, B, C, D, E, F. These are the vertices. 0, 3, 5, 7. Now I want to use smallest channel number. So I make this channel 1, channel 2. Now once I have 1, so this can be 3, because once I have 1, I cannot have 1. 1 plus 3 is 4, 1 plus 5 is 6. So I cannot assign these numbers to any of these, but I can assign 3 there. You can check. I am going to leave that as an exercise. This is the best spanning color. In a sense, smallest span. That means you cannot color this with smaller numbers than this. For example, if I have 1 here, 1, 4, 2, 8 are gone, 6, 8 are gone. Once I color with 2, I cannot use colors 2, 2 plus 3 is 5, 2 plus 5 is 7, 2 plus 7 is 9. Once I use color 3, anything adjacent to 3, I cannot give 3 plus 3 6, 3 plus 5 8, 10. I cannot use these colors. So the smallest number of smallest number which is can be assigned to a vertex is 1, 2, 4, 1, 3, and 11. I want to leave this as an exercise for you to look into it. So this is one way of efficient T coloring. In a sense, the difference between the largest channel number and the smallest channel number should be as small as possible. That means it can be easy for you to go from one channel to the other. So these are all different variations of vertex coloring, which you are going to see a lot in applications. And there is another variation which they talked about in the book, that is called the K-tuple coloring. And I want to leave that as an exercise for you to read. So please read these. Okay, please read these examples on these pages. So that talks about K-tuple coloring. It is not very difficult for you to follow. So this is an exercise for you to read. Please go through that. Now, there are still like 15 more minutes I need to cover, but I want to stop this video at this point of time because I have to go to a class. So I'm going to upload this, and the rest of section 3.3 I will post it in another video sometime today. That video will not be this long. So I will stop at this point and I will stop sharing this. So section 3.3 you will see two videos. One is covering the first half and the other is going to cover the second half. So I will stop share at this point. Thank you so much. I am saving it. Now I'm going to stop the recording.